Hi friends, a very good evening and thank you for joining in today. Could you please confirm in the chat window if you're able to see my screen and hear my voice clearly? Can you please confirm that so that we know that there are no technical glitches and we can get started with the session? Can you please confirm in the chat window if everything is all right? If you can hear me, hear my voice, and of course see my screen. Okay, cool. Okay, let's wait for a minute or so. A couple of things as students were asking. So you can go to gate.iitb.ac.in because IIT Bombay is the organizing institution for this year for GATE 2021. Their online application processing system is open. So if you just click on this, it will take you to their candidate login page. Just log in, fill up all the details here so that you can register for the GATE exam. Right. So if you go to their important dates, they actually mentioned that the portal or the GATE online processing system opens on Monday, which is 14th of September, but it seems to be open right now. So we were just checking it just a while ago. So here is the portal. So just very simple, just type gate.iitb.ac.in, right? So very simple. So it will take you to this home page. So if you just type gate.iitb.ac.in, the very first thing which has a new blinking here, which is application processing system. I recommend everyone to apply as soon as you can, and because I think the last date is the end of the month, no? So let me just look at the dates. Yes, the last date for regular online registration via the application portal is 30th of September. So please try to do it before it. Why not do it right away? Right after this, you can always do it and finish it off. Of course, the rest of the dates are also here. You can just read up about it. Right? Cool. Sounds good. Just let me look at the chat window on my computer. Yeah, so everything is fine. Good. So please don't forget to apply for GATE. Okay, so that you can take the GATE exam in February. Right? Tentative. Again, they've put the tentative dates, but most likely they'll stick to this with minor modifications, unless there is something major happening at that point of time. Cool. Okay, folks, thank you very much, and let's jump into the discussion itself. This was one of the announcements that I quickly wanted to make since students were asking for it. So just give me a second. Just give me a second here. Okay, cool. So let's start with the live session. Hope no glitches. Okay, some of you have already registered. Very good. I mean, it's just a standard form that you can fill. So nothing rocket science out there. Okay, just make sure you don't make mistakes because that can be costly. Okay, so today is the second live session for computer networks where we'll cover some of the questions from network layer, some questions from transport layer, some questions from application layer. Obviously no security because it's been removed from GATE 2021 syllabus. Okay, so these are the three topics, and this is the last live session in the first iteration of all the subjects. With this session, we would have completed all the subjects in GATE syllabus, at least 2 sessions for every subject, some subjects even 3-4 sessions, right? So this will, as I think our initial plan was to complete it by September 15th, at least the first iteration, and we are perfectly on track with this. So that's a good thing, no delays there. So let's, okay, a quick recap. I've mentioned this in the previous session also. So we will have a network layer. So we'll have some questions from network layer, some questions from application and transport layer. So certainly security is not there, but typically 1 mark is given, on an average 1 mark is given from security. That 1 mark could be allocated for other topics also. Okay, some students are asking if we can do general sessions. We'll certainly do public sessions even after this. Public general sessions, we'll try to do as many as possible, but there will also be a considerable number of private sessions for our course registered students. Okay, sounds good. Very good. Okay, cool. So let's dive into the questions, right? So let's start with some easy questions. Let's focus on the questions. Anything that I'm not able to answer here, please always reach out to us over email. Cool. So here is the first question. Let's start with some simple questions first. This is an easy question because nothing is mentioned, this is an MCQ. Okay, very simple. If it's an MSQ, we will clearly mention that. Please read the question carefully. Look at each of the options carefully. Again, we are starting with some easy questions today. Of course, we'll go to some medium questions also. Please read all the options carefully because the question says which of them is not true. Okay, so please read it carefully. Again, DHCP is something that all of us use extensively in our day-to-day internet connections. Vishwesh is asking, are these points covered in the videos? Yes, in lots of detail. Yes. So we have covered, actually we have covered more syllabus than what is needed for GATE, just in case, for the worst case scenario. So we are always conservative. We try to cover slightly more than what has been asked in the past. So yeah. Okay, sounds good. So let's get into the discussion and let's answer this question. So DHCP, we all know what it is. Very simple concept. If you know it, this is a trivial question actually. But questions like this have been asked in the past for about 1 mark. Addresses are leased to the hosts. Yes. A host will usually keep the same address by periodically contacting the DHCP server to renew the lease. Exactly, that's how DHCP works. So this option is correct, but since the question is not true, this can't be the answer. Dynamic host configuration protocol, yes, DHCP, assigns and renews IP addresses from the default pool. Yes. Okay, this is a protocol. DHCP is the protocol that's used, right? So in the DHCP operation, if an address conflict is detected, the address is removed from the pool until the conflict is resolved. Yes, right? The router which is allocating these IP addresses, right? So, or the server which is allocating these IP addresses will resolve it before the conflict is resolved by the central server which is giving your DHCP, which is giving you the dynamic IP addresses, right? So this is also true. Obviously, the only option left is D, right? So DHCP addresses are allocated after a negotiation between the server and the host to determine the length of the agreement. No, this is not how it works. A is how it works. Addresses are leased by the hosts, and periodically the host typically reaches the server to renew the lease. Okay, this is how A is how it works, not D. So since the question is not true, D is the right answer. Very simple. If you know how DHCP works, this is a very simple, straightforward question. Okay, cool. So let's go to the next question now. Okay, again, something very simple, basic stuff about IPv4 headers. Let's start with a few easy questions. Again, a very simple question. Please read each of the options carefully. This is not an MSQ, this is an MCQ because nothing is mentioned here. It's not mentioned that it's an MSQ. So it's a simple MCQ. Again, please read all the 4 options. There is also none of the above. So please read all the options carefully. If you know how IPv4 headers work, how the checksum is computed, I think you can answer this. There is some amount of facts that you have to remember here. Yeah, so with respect to these protocols, there are a bunch of facts that we have to sometimes remember. I mean, I don't like remembering facts. I like I like more foundational stuff, but sometimes you have to know this. Okay. Please read all the 4 options. Okay, a good chunk of you have put in the answer. So let me go ahead and explain the solution. So which of the following is true, right, about IPv4 header? The checksum field changes in the IP header during the IP packet forwarding by the router, right? So look at this. When a router forwards an IP packet, what does it do? Look at this, right? The router decrements the time to live. When the time to live is decremented, the IP header has changed, right? Which means, look at this, the whole IP header has changed, right? So the router has to recompute the header checksum, right? So the header checksum, because IPv4 has header checksum, right? So the router decrements TTL. Once it does that, because the header has changed, it has to recompute the header checksum. So checksum field changes in the IP header during the IP packet forwarding by router. Yes, it does. So this is obviously the right answer. But let's look at the other options also, just to make sure that we are not making any mistakes. What is B? B says, for the minimum size header, the HLN bit should be 0100. No. So the minimum is 01. So the HLN bits, right? The header length bits are 0101 to 4 ones. Because this corresponds to 5 and 5 into 4 is 20 bytes, right? So this corresponds to 15. 15 into 4 is 60 bytes, right? So the smallest value is 0101, not 0100, not 4. The minimum value is 5. Okay, so obviously this is not true. The IPv4 header have checksum only for payload. No, they have header checksum also, right? There is also a header checksum in IPv4, no? So obviously this option is not right. Since one option is correct, none of the above can't also be the right option. So A is the right option. Okay, here all you had to know was that a router decrements TTL and it updates the whole header checksum. If you know these 2 facts, this is a straightforward question, right? Simple, straightforward question. You have to know this fact that the router has to reduce the TTL, right? It does, right? In IPv4. Cool. Again, we are starting with some simpler questions. Okay, here is it's a numerical question and it's of medium hardness. This is a very good question. Typically questions like these are asked for 2 marks in GATE, right? So here is a third question. It's a numerical answer type. So you have to fill the answer here. It's a good question. So just try to think about it from the first principles. Think what is a token bucket, what happens in a token bucket. Think from first principles, try to draw diagrams, and this problem is simple. Again, please be very careful, draw the diagrams. If you understand how token bucket works internally, this should be simple to solve. But please be careful. I see a lot of students just applying some formulae from some textbook or some notes that they've written. Please don't do that. Think from first principles. Think from the basics. Try to draw a diagram if that helps you. If you know how a token bucket works, this is a simple aptitude problem. Again, questions like these are typically asked for 2 marks in GATE. So if you carefully solve it, you'll get the answer. It's not hard. It's simple. If you know the concept, it's very simple. Please take your time. Don't be in a hurry. please work it out carefully. I see people making mistakes. Some, not all. Okay, folks, please try to solve the problem. Any questions you have outside of this, please email us, we'll answer that. And after you solve this question, between two questions, I can answer a few general questions. I'll try to, based on the time. Please focus on solving the problem. Because I see very few answers being put out, only a few of them. Are people stuck with this question, or are people not able to solve this question? I'm looking at the chat window. Okay, maybe it's just better if I solve it for everyone. Okay, I think some of you are stuck. Some of you have wrong answers. Some of you certainly have correct answers. Okay, so let's dive into the question. Okay, so I'll explain this. So you have a host machine that's using token bucket algorithm. So you have basically a bucket like this with tokens, right? For congestion control. Okay, the token bucket has a capacity of 2 megabytes, right? So already so its total capacity is 2 megabytes worth of tokens, or it already has the maximum output rate is 15 Mbps. So if you have any data, suppose you have some data in a buffer here, right? Suppose you have data in a buffer, the maximum output rate is 15 Mbps. Okay, 15 megabytes per second. Yes, good. Right, so this is the maximum output rate for the data. Now token arrival rate is 10 megabytes per second, right? So tokens can arrive at 10 megabytes per second, right? And the maximum speed at which data can be sent out, right? The maximum output rate is 15 Mbps, right? And again, for every byte of data that is sent out, you need a token. That's how that's how your token bucket congestion control works, right? So the token bucket is currently full. Okay, so all the 2 megabytes worth of tokens are already there. So we already have 2 megabytes worth of tokens. Okay, the machine needs to send 10 megabytes of data. So in the buffer, we already have 10 megabytes of data. We already have this. We want to send it. Okay, so this is the current situation. The minimum time required to transmit the data. Okay, let's tackle it. Forget about formulae. Let's try to do it from first principles. Okay, so look at this. If you think about it, there is already 2 MB of tokens here. So let's take 1 second, right? If you take 1 second, in 1 second, 10 MB of tokens will be added to this bucket. But from this bucket, because the maximum output rate is 15 Mbps, it can consume 15 MB worth of tokens at any time. So if you look at it, the input rate, if you look at this bucket, right? If you look at it like a water, like holding some water, right? So you can dump in, and if you think bytes as some droplets of water, right? So 10 megabytes will come in any second, and 15 megabytes can be consumed in every second maximum. and we are asked the minimum time, right? So let's assume the maximum output rate is used, okay? Which means if you think about it, on an average, so if you look at this 2 MB, okay, so if you look at it, the input, so think about it as a bucket, right? 10 MB per second is the input, output is 15 MB per second, which means you can drain all of this bucket. The output rate, the net output rate is 15 minus 10, which is 5 megabits per second. Okay, that's the rate at which you can consume all of this 2 MB worth of tokens that you have. Okay, the data that you want to send is 10 MB, right? So in this 10 MB, let's break it into 2 MB and 8 MB. Because for 2 MB, you already have all the, look at this, for 2 MB, you already have all the tokens. Okay, and for this 2 MB, you can keep using the 15 Mbps. And while you're using this, there is also new tokens being generated, right? So to consume 2 MB worth of tokens or to transmit 2 MB worth of data, so total data you have is 10 MB, right? To consume 2 MB worth of data at 5 Mbps throughput, how much time do you need? Very simple, 5 MB per second. So 2 MB will take 0.4 seconds. So which means in 0.4 seconds, we would have consumed all of these 2 MB worth of tokens and made the whole bucket empty, right? So first thing is 0.4 seconds. In 0.4 seconds, all these 2 MB worth of tokens are consumed. Very simple. And the bucket would be empty. Once the bucket is empty, whatever is your output rate, right? You can only transmit at the rate at which you're going to get your tokens, right? You can't do anything better than that, right? So one second. There is a small catch here. Okay, there is a small catch here. 1 second. So your 10 MB of data, 1 second. Because in this, okay, let me write it down slightly differently. I'm just trying to break it down into first principles. Okay, you have a total of 10 MB of data. In the first 0.4 seconds, right? Look at this, in the 0.4 seconds, some data here is consumed, right? Some data from here is consumed, no? And this data is being sent at 15 megabits per second, okay? Because we have excess tokens here, right? So in 0.4 seconds, this whole bucket would be empty. But for 0.4 seconds, you can transmit data at 15 Mbps because there are tokens available here, right? So 0.4 into 15 Mbps into 15 Mbps. This will give you how much? 6 MB of data. So in the first 0.4 seconds, you are not transmitting 2 MB. I'm sorry. Okay, you're transmitting total of 6 MB of data. Okay, because in the first 0.4 seconds, there is also new tokens being created here, no? There is new tokens being created here, all the data that you have in the buffer, and you can transmit at full speed because there are tokens available here. So for the first 0.4 seconds till the time this bucket becomes empty, you can transmit at full speed of 15 Mbps, which means of this 10 MB, 6 MB will be transmitted. Now you're still left with 4 more MB. At what speed will this 4 MB be transmitted? Now you don't have any tokens in your token bucket. Your token bucket is empty, but tokens are generated at 10 Mbps, which means even though your maximum output rate is 15 Mbps, you can only send data at 10 Mbps because tokens are available at 10 Mbps, right? So this 4 MB will be sent at 10 Mbps. Now, if you're sending data at 10 Mbps, 4 MB would take 0.4 seconds, right? So what is the total time that it has taken now? 0.4 seconds to transmit the first 6 MB of data till the time the token bucket is empty. Another 0.4 seconds to transmit the remaining 4 MB where you're transmitting data at the bucket input rate, right? So the total time is 0.8 seconds, which means option C is the right option. Okay, very simple, clear, right? I hope this is clear. Okay, is this clear, folks? Just wanted to make sure. This is a little bit tricky. Intentionally, we have given it. So is this clear? Is the solution clear? Can you please confirm? Can you please confirm if the solution is clear? Okay, so people are still not sure. Okay, let me re-explain it. Okay, so initially you have a token, you have a bucket with 2 MB, right? Your total data is 10 MB, right? You're getting data in at 10 Mbps. Okay, you can consume data at 15 Mbps. Okay, this is the total data that you want to send. This is the buffer that you have because you're getting, and this whole 2 MB is full. Okay, so this whole bucket is full, which means now look at it this way, right? So for some period of time, for some delta t, let's call it delta t, right? You can transmit data at 15 Mbps till the time this bucket is not empty, right? Till the time this bucket has tokens, this can keep consuming, you can keep transmitting data at the fastest speed. And the maximum speed you can transmit data or send data out is 15 Mbps, right? So if you look at this, the input rate is 10 Mbps, the output rate is 15 Mbps, right? Which means the net outflow rate is 5 Mbps. So net outflow rate, okay, net outflow rate is 5 Mbps. So if your net outflow rate is 5 Mbps and you have 2 Mbps to 2 MB of tokens to start with, in how much time would you, let's assume in delta t time, this whole bucket will become empty. In how much time would this bucket become empty now? Okay, look at this, 2 MB, it takes 5, see your net outflow rate is 5 MB you can empty in 1 second, which means 2 MB you can empty in 0.4 seconds. Think about just like a water bucket. Okay, and water coming in, there is a water pipe coming in, water pipe going out, except that instead of water you have bits and bytes. Okay, so at the end of 0.4 seconds this token bucket is empty, but in this 0.4 seconds how much data from the buffer were you able to transmit? Because you're transmitting at 15 Mbps, right? 15 into 0.4, 6 MB of data, 6 MB of this 10 MB has been transmitted at 15 Mbps speed. Now you are still left with 4 MB of data that you have to transmit. This 4 MB of data will be transmitted because the bucket is completely empty now. This 4 MB of data will be transmitted at the same rate at which the tokens are coming in. Look at this, the tokens are coming in at 10 megabytes per second, right? Even though you can send data at 15 megabytes per second, till the time you don't have tokens, you can't send data out. So this 4 MB of data which is still left out will still be sent at 10 Mbps only. So if you're sending data at 10 Mbps, to send 4 megabytes takes 0.4 seconds. So from the time you started, for the first 0.4 seconds, you're transmitting 6 MB of data at 15 megabytes per second. The remaining 4 megabytes, you're transmitting at 10 megabytes per second, and it takes 0.4 seconds. So the total it takes is 0.4 plus 0.4, 0.8 seconds. Is this clear? Okay. Is this clear? This is one way of solving it. Again, there are many ways of solving this problem. I'm trying to break it down and come from the basic first principles. This is one way of solving it. Is this clear, folks? Okay, cool. So I think most of them got it right. So cool. Again, this video will be available again on YouTube, so you can always check it. Intentionally, we give some slightly tricky questions so that you're better prepared for the GATE exam. And questions like this you can expect in GATE exam for 2 marks easily. Okay, again, this is at the end of it, if you think about it, this is a basic aptitude problem. If you know how token buckets work, this is an aptitude problem, and there are many ways of solving the aptitude problem. Okay, cool. So let's go to the next question now. Oh, this is a standard question about non-blocking switches. This is a very theory-like question. But questions like these have been asked in previous year gates, typically for 1 mark. Again, these are types of questions where if you know about a non-blocking switch, you can answer, otherwise you'll not be able to answer. These are very, what should I call, fact-based questions rather than problem-solving based questions. Okay, I see a few of you putting in your answers. Good. I guess we have covered about switches in lots of detail in the course videos, if I'm not wrong. Okay, most of you got it right. It's a very simple question. Of course, you have to know what is a non-blocking switch. Again, those of you who don't know, you can just do a quick Google search. There's also a nice Wikipedia on non-blocking switches. So option C is the right option. Again, this is a very fact-based question. Okay, you either know it or you don't know it, right? Again, in case in an examination setting, if you don't know something like this, because this is an MCQ where there is negative marking, just avoid it. In case you don't know. Okay, in case, I'm just saying, because some fact-based questions, it's sometimes hard to remember all the facts, or you may have forgotten some of the fact-based questions. So in case you don't know this, it's best to skip it. Okay, cool. Let's go to the next question. Before that, there is one point that I wanted to explain. Since all of you are here, I was just telling about this. One second. So since many of you have joined here, just a quick note, please go to gate.iitb.ac.in and please register for the GATE exam. Okay, so the registrations have opened, and if you look at the dates, the registrations, the official date is 14th September, but they've opened the registrations from today, and you can register till 30th of September as regular registration, right? Okay, so very, very importantly, please don't forget to register, because then all this effort goes into the drain. Okay, please register. Just wanted to call it out in between also. So another question that some of the students are asking is about the next live sessions. Some of them will be public, but a vast majority of them will be private. Okay, for all of our course registered students. And number one. Number two is very, very importantly, for each of the live sessions that we conduct, some of them will be problem solving sessions. Again, that's what we've been conducting. We'll also conduct some general live sessions on how to revise, how to better prepare for a topic and things like that, right? So that's another type of sessions that we'll do. Some of the general sessions, we'll try to certainly conduct them publicly. Some of the private sessions will be only for our course enrolled students, right? So again, for the topics, we will announce them well in advance, just like the current sessions. We typically announce them at least a week in advance, roughly a week in advance. And we announce all the live sessions of a week well in advance so that you can come prepared for them. Okay, so don't worry about it. Cool. So, this is a good question. This is an MSQ, folks. Okay, please remember, this is an MSQ. Please read the question carefully. Which of the following is or are not true? This is an MSQ, which means multiple options can be correct. Again, please think of the TCP state diagram. This is all about the connection closing part, right? Whether it's active connection close or passive connection close. We think questions like these could be asked as MSQs because they can test your whole knowledge of the TCP state diagram in just one question this way. Please read the question, folks. Which of the following is not true in TCP? Please read the question. Which of them is not true in TCP? Which of them is not true? Think about the state diagram. The connection closing part of TCP state diagram. This is all about that chunk, those states there. Okay, I see a few of you putting in your question answers, but waiting for others to also to do it. Again, we guess questions like these could be asked. Again, we have seen similar questions in earlier sessions also, where MSQs, in a single MSQ, the examiner can try to test your knowledge of a whole concept. In this case, they're trying to test your whole understanding of TCP's connection close. This will make MSQs like a good test of your depth of knowledge and your good understanding of the whole concept itself. We have done similar questions yesterday also, right, for MSQs. Again, we don't exactly know how MSQs will turn out in GATE because it's completely new from this year. But looking at other exams that IITs conduct, we think this could be one way. Okay, I see a lot of you putting in your answers, so let me just go through it. Okay, so just in the interest of time, instead of drawing everything, I have taken this diagram from Wikipedia. Okay, this is the same diagram that we explain in our course videos also. This is the TCP state transition diagram from Wikipedia. It's a finite state automator, right? So let's go. So what is being asked here is this. Let's look at each of the options. In the fin wait 2 state, acknowledgement of the first fin is received, waiting for the second fin. Where is fin wait 2? This is our fin wait 2. Okay, look at this. The acknowledgement, so the acknowledgement is received. Look at this, the acknowledgement is received here, right? So, and it's waiting for 1 second. In the fin wait 2 state, acknowledgement of the first fin is received and waiting for the second fin. Again, we have also listed down this here. Okay, so this is the state transition diagram and this is the description of each of the states. Okay, so this is taken from Wikipedia. So if you look at fin wait 2 state, that's the question, right? It's fin wait 2. Yes. So in fin wait 2, acknowledgement for the first fin received, waiting for the second fin. Look at this. Yes, right? So look at this. So fin wait 2, when do you arrive at fin wait 2? You got the fin signal. You also sent the acknowledgement back, right? So you are waiting for the second fin. Right, so acknowledgement for fin 1 is, look at this, that's why I've also pasted this description here for you. Fin wait 2 is, again, you can figure that out from the diagram also. You already got the first acknowledgement, you're waiting for the second fin. Okay, the finish basically. Okay, so fin wait 2 is acknowledgement for fin received, waiting for second fin. So this statement, in the fin wait 2, ACK for fin is received, waiting for second fin. Yes, this statement is true, and hence it can't be the answer because it says not true, no? So A can't be the answer. Now let's go to B. In the last acknowledgement state, first fin is sent and waiting for acknowledgement. Okay, so where is last acknowledgement? Again, we have also written it down here clearly. Okay, so this is your last acknowledgement. In the last acknowledgement, what is happening here? The second fin is sent, right? And you're waiting for acknowledgement. Okay, the second fin, see, last acknowledgement, which is part of the passive close. So the whole question is about the active close and the passive close states. So the last acknowledgement is part of the passive close. Again, we explain this in a lot more detail. We almost spend, I think, 40 minutes explaining just this state transition step by step in the course videos. I will not be able to do it in this session because this is mostly a problem solving session, right? I'm assuming that you know the state transition diagram. Okay. So the last acknowledgement, basically, if you want to look at the description of it, second fin sent, waiting for acknowledgement. Okay. So what is given here? In the last acknowledgement, the first fin is sent and waiting for acknowledgement. No, so it's a last fin sent. No. So there's a problem here. No. Look at this. In the last acknowledgement state, one fin is sent, other fin is also sent. So second fin is also sent, not the first fin. No. So B looks like an incorrect option. In the last acknowledgement state, first fin and second fin, both of them are sent and you are waiting for the acknowledgement. Okay, so this statement is incorrect. So B is an answer. Okay, so let me, okay, so I'll tick it later. So A can't be the answer because it is true. The question is saying which of them is not true. So B is not true. What about 3? In the time wait state, the second fin received and acknowledgement is sent. Okay, in the, so what is that state? Time wait state, right? Okay. So where do you have your time wait state is the last one. It's literally the last state in the active close part, right? In the time wait state, second fin is received, acknowledgement sent, waiting for 2MSL timeout. Okay, standard logic. You're just waiting for timeout to happen so that you can close the connection. So what is the statement given here? In the time wait state, the second fin received and acknowledgement is also sent. Yes, everything is sent. We are just waiting for timeout to happen to close the connection. So this statement is also true. Hence, it can't be the answer. Now, what is the last one? In the close wait state, first fin is received and acknowledgement is sent. Okay, where is the close fin? Close wait, right? The question was about close wait. Okay. I get confused with this terminology very often. So whenever I have to solve a problem like this, I just try to draw this diagram. Okay. If you practice it, you'll remember it very easily. In the close wait, what is happening? Look at this. In the close wait, the first, so that's why I've also written it here. In the close wait, first fin received, acknowledgement sent, waiting for application to close. Okay. So first fin received, close wait is first fin received, acknowledgement sent. What is the statement here? Oh yes, in the close wait state, first fin received and acknowledgement sent. So A is correct, C is correct, D is correct. These statements are correct. So see, look at this. This statement is correct, this statement is correct, this statement is correct. This statement is incorrect. And the question is saying which of the statements are not true. So B is not true, right? So again, questions like this require you to understand the state transition diagram. I think I've also mentioned it in the course videos when I explain this diagram, that you have to understand each of the states and you should be able to draw this on your own. Okay, please, when you're learning the state transition diagram, it's very important to understand every transition, every state that is there. Because questions like this, not in MSQ format, but in previous formats have been asked. Okay, and I can imagine questions like this. Imagine if we were setting up the paper, this is one question that will test your complete knowledge of TCP connection close. Okay, cool. Again, Vishesh is asking, how do you remember this? Again, it's not very illogical, right? It's a very, very logical thing, right? Just check out the course videos where we explain why each of the states exists and what is being sent. So this whole state transition diagram, if you look at it, it looks complicated. But if you break it down into bits and pieces, it's very simple and easy to remember. That's what you should also do as part of your revision. This diagram is extremely important based on previous year questions. Okay, please, there are some facts that you have to remember. But this is not such a hard fact because this has logic behind why it is designed like this, which we discuss in the course videos. Okay, cool. So let's go to the next question. More numerical questions now. Okay. This is about congestion control. Okay, got it. Just be careful here with the congestion control. Okay, it's already 7:43. Okay, we might have to overshoot this. Okay, let's focus on solving the questions now. Okay, because there are a few numerical questions which are interesting to solve. So let's solve them. It's already I just didn't keep track of the time. Please focus on solving the question. Any general questions you have, feel free to email us and we'll try to answer as best as we can. Again, if you understand the congestion control algorithms that TCP uses, this is actually fairly straightforward. Remember, when does timeout happen, right? What happens when timeout happens in congestion control? Again, this problem is also a very simple. This problem is also a very, very simple question, and of course, you have to understand how TCP congestion control itself works. If you know it and if you know the key cases, this is an aptitude problem again. Again, it's very easy to make a silly mistake here. Again, your problem solving skills will only improve if your foundational concepts are strong and if you have practiced enough problems. There is no escaping that fact. Even when we have to solve problems like these or set up problems for different subjects, we revise the subjects. Like before solving the computer networks problems, I would sit down with my notes, the whole notes that we have, revise everything, anything that I've forgotten. I would go ahead, watch my own videos sometimes or read the textbook sometimes, right? So please remember that you have to revise, you have to understand each concept and practice. Cool. I think a good chunk of you have given it a shot. So let me try to explain the solution step by step, right? So first and foremost, let's write down all the facts that we have. Okay, first and foremost, what do we have? Maximum segment size is 2 KB, right? So one maximum segment size, right? One segment is maximum 2 KB. This is a very important fact, right? So we are given the TP is 50 milliseconds. The propagation time is 50 milliseconds. Okay, then and let the size of the congestion window be 40 KB. Okay, so the congestion window is of size 40 KB at timeout. Okay, when a timeout occurs. Okay, at the time of timeout, because this WC keeps changing, right? So at WC you had a timeout. Okay, so at this time, at this when WC is 40 KB, you had a timeout. So what does timeout imply? As we have discussed in the course videos, timeout basically implies a severe congestion. Okay, so you have to know this part of the concepts. Okay, it basically implies severe congestion. When you have this severe congestion, what do? You change your threshold window size as WC by 2. Sorry, let me just write it carefully. So this is the, so when you have timeout, right? When you have severe congestion, what is done here is the threshold window size is changed to WC by 2. And then you slow start, right? This is what happens when you time out, and you have to know this part of the system of TCP congestion control. If you know this, then rest of it is fairly straightforward to solve. So let me solve the rest of it for you. Okay, so because we have a timeout, your W threshold will become WC by 2, which means it becomes 20 KB, right? It becomes 20 KB and you're going to slow start. Okay, now in the first transmission, let's write down. Okay, let's write this as transmission number, and let's write down the bytes that are transmitted. Okay, because we are slow starting here, right? In the slow start, what do? First, we only send, in the first transmission, we only send one segment. This is your segment size, no? This is your one segment size, right? Or maximum segment size. So in the first transmission, we'll start with one segment, which means we'll transmit 2 kilobytes. Okay. because we are doing slow start. Look at this. We'll do slow start with a threshold window size of 20 KB. Okay. Then, okay, in the second transmission, okay, we will send in the first transmission, we sent one segment. One segment is 2 KB. In the next one, we'll double it, right? So we'll send 4 kilobytes, right? Because we're going to send two. So let's write down. First transmission, one segment, two segments, right? Then in the third transmission, let's see, 1 second, is everything all right? In the third transmission, we should do 1 second. So in the third transmission, just a second here. Maybe I have a small error in my system. Just give me a second. Let's solve it together anyway. In the third system, we will have 8. 1 second. Let me just go here. In the third one, we will have 16. So in the third one, we'll have 16 KB, right? In the third transmission. In the fourth transmission, we will have 20 KB. We can't go beyond 20 KB because our threshold is 20 KB itself. Look at this. Our threshold is 20 KB itself, right? So we can't go beyond 20 KB, right? So what we have here is 1 second. 1 second. Let me just go step by step. I think this should be. Let me just do it from scratch. I think I made a small mistake when I'm solving it. So in the third one, it will double. It will become 8 KB. In the fourth one, it should become 16 KB. In the fifth one, it will become 20 KB, right? Because you can't double it anymore, right? Yes. This should not be. Sorry, I jumped to 16 directly. So first transmission, I'm getting slightly confused because the segment size is 1 KB, right? So 1, 2, 4 into 2 is 8. Then 8 into 2 is 16. In the fifth one, yes. In the fifth one, you can't go beyond 20 KB, right? Because your threshold size is this. After 20 KB, what do you do? After 20 KB, you can only start sending 2 KB each, right? Because after you reach W threshold, what do? You increment by 1 MSS. Okay. Next, you will send 22 KB. What is the total data that we have to send? Okay, we have to reach 30 KB, no? Okay, we have to reach 30 KB. Okay. Then we'll send 24. Then we'll send 26. Then we'll send 28. At the 10th interval, we will reach 30. Okay. Yes. Yeah. So from here, we are doubling till the time we reach W threshold. And then the congestion control basically says, so we are slow starting, doubling, and then so this is how it has to go. Yes. So now if you look at it, this is all right? Yeah, I think 2, 4, 8, 16. Yes. So I think I directly wrote 16 here, which is not correct, right? So now what happens? So at the 10th transmission, we reached 30, right? So now the question here is the total time taken. Okay, so the total time taken by the TCP congestion to get back to 30 kilobytes congestion. Okay, so let me just use a different color here to get back to 30 kilobyte congestion window. So let's assume at this time there is a problem. Again, remember how much time, because our propagation delay is 50 milliseconds. Okay, what is our round trip time? Our one round trip time is 2 times propagation delay. Right, our round trip time, you have to go and come back. No, our round trip time is 2 times propagation delay, which is 100 milliseconds, right? Which is 100 milliseconds. Now for us, look at this. For us, the time taken by the TCP connection to get back to 30 kilobytes congestion window. Okay, so this is 1 transmission, 2 transmissions. So total of 9 transmissions have happened, right? At the end of 9 transmissions, right? Because you need a total of 9 transmissions, right? So because you finish only in your 10th transmission, you will be sending 30 kilobytes of data, right? Again, so for 9 transmissions, you're not sending 30 kilobytes, which means to reach a 30 kilobyte congestion window, you have to complete 9 round trip times. 9 round trip times takes 900 milliseconds. Because 1 round trip time takes 100 milliseconds, right? So this is cool. This is cool with everyone. Again, I wrote 16 earlier, so I corrected it. So for you to reach So this takes one round trip time. So 9 round trip times have to be completed, which means you have to completely finish 900 milliseconds of time for 9 round trips to happen. 9 round trips will take 900 milliseconds. So it is just this transmission number which is important. So the right answer here is 900 milliseconds. Okay, I was just doing it slightly slowly because I did a small mistake of putting in 16 here. It should have been 8. Okay. Again, one of the pieces of confusion for questions like this is if this is not 1 kb, no, because when you learn it, we learn the running example that we solved even in the course videos is maximum segment size is 1 kb. The moment it becomes 2 kb, you start getting confused slightly. Okay, cool. Somebody saying, don't we count the time for the 10th for the 10th round also? No, we don't have to count for the 10th one, right? Because all we are asking is connection to get back to 30 kilobyte congestion window, right? What is happening? See, after you complete the 9th transmission, right? After you complete the 9th transmission, the WC will get updated to 30 kilobytes. You don't have to transmit the 10th connection itself, right? So you don't have, at the end of 9th transmission, after you transmitted the 9th one, after you finish the 9th transmission, the WC will get updated to 30 kilobytes. You don't have to complete the 10th transmission. After the 10th transmission, it becomes 32 kb. Okay, that's the important difference. Okay, I hope this is clear. I know it's confusing. Some of you have answered 1000 milliseconds, and I can see why you made that mistake because you also counted the 10th transmission time. But as soon as the 9th transmission is completed, you would update your WC, no, to 30 kb. You would increment it by your maximum segment size. Okay, I hope this clarifies the question. Okay, let's go to the 7th question now. This is a straightforward question about NATs. Folks, I don't think we can complete by 8 p.m. today. Just like the previous session, we might have to overshoot a little till about 8:15. Okay. Again, please read all the 4 options. It's an MCQ. Again, please read all the 4 options. Again, it's an MCQ, it's not an MSQ. Please read the options carefully. Okay, so let's give it a few more seconds and then I'll answer it. Again, any question that you think is not, the answer is not right, please email us. If there is a mistake, we'll correct it, or else we'll explain you why we think your answer may not be right. Okay. Okay, so let me answer this question. Again, just for the sake of clarity, I've taken this image from, where is the image? Okay, so I've taken this image from Wikipedia. Okay, this is the image for a router which has network address translation. Again, this is the same image that we use in our course videos also to explain how NAT works. Okay, so notice that, okay, so let's read each of the four options that we have. So the question says which of them is false, right? So let's write down. A NAT enabled router represents an interface of a private network to the internet. Yes, right? So that sounds perfectly true. It is sufficient that a NAT enabled router translate the IP address of the host inside the LAN to its public IP address before sending the packet to the internet. This is not sufficient. Because look at this. If you think about how a NAT works, it has to do both sides. So what this is saying here is it is sufficient. Just this much is sufficient. So what it is talking about is it is saying when a packet is being sent from the private network outside, you just have to do the address translation. Not just that, right? If a packet is coming from the internet back to the private network, you still have to again fix it, right? So this is only half the job that a NAT does. So this is saying it is sufficient that a NAT enabled router translate the IP address of the host inside the LAN to its public IP address before sending the packet. This itself is not sufficient, right? Because when a packet comes back, also you have to fix it, right? There are two parts to it. Okay, so this statement is correct. This statement is not complete. Just this much is not sufficient. Next, a NAT is a solution to solve the scalability problem of IP address. Yes, that's why we have NATs. A host behind a NAT enabled router cannot have a public IP address. Yes, because if you have something, so this statement is also true, right? Because look at this, if you have a NAT system, right? So the public IP address of everything that is coming from this private network will be 150.150.0.1, right? In your NAT, you have the network address translation tables, etc. to do the address conversion. But this host will not have a public IP address. The public IP address for the whole thing will be the same, which is the router's 150.150.0.1 here, right? So a host within the private network cannot have a public IP address, right? The host behind the NAT enabled router cannot have a public IP address. It will only have its own private option. It will have its own private option, and the NAT's public IP address is what is given to all the hosts behind the router, right? So this option is right. This option, the solution, this is also right. This is also right. This is incomplete. This statement is incomplete. Just this is not sufficient. Just this much is not sufficient. Okay. You also have to do, so what this is talking about is when you're going from your host, so suppose there is a NAT here, there is a router NAT. This is your whole internet. Okay. This is your private network. While going from here to here, yes, what it says is right. But this alone is not sufficient. While coming back also, we have to take care of it. We have to do the reverse address. So we have to translate to the private network address when it is coming back also, right? So that's another part that we have to analyze. So this statement is the closest to being incorrect. So B is the right option. Okay, cool. Let's go to the 8th question now. Okay, so this is another fact-based question. So this is another MSQ. This is all about HTTP protocol. Again, this is I think some of these, this is an MSQ, folks. Please remember that it's an MSQ. It's already 8:03. We have 3 more questions. Okay. Some of them are, you have to solve problems. Again, our mentors are answering some of the follow-up questions that students have in the chat window. In the previous question, we had to pick the one which is least correct. That's why we picked B. I think one of you has this question, so just elaborating on that. Again, in MSQ, you have to get all the options correct. Partial correctness will not give you any marks. Again, this is another question where Vishesh, I think you don't understand the objective here. If you start spending half an hour, 1 hour on each question, we can do live sessions for 10-12 hours. Okay, so the objective here is to solve 10 problems in 1 hour. Please understand that. Okay, and you have requested me to recap one question and I did that. Now, if you want me to spend 1 hour, I can spend 1 hour just on this question. So please understand that people don't have time. Not me, the students. I can spend 10 hours answering each of these questions. We've already elaborated the answer in detail. If there is a follow-up question, email us. We're also answering questions in the chat window. And if you have come ill-prepared for this session, you have to be blamed for it. Again, we have already overshot on time here. Please understand that we want to complete 10 questions in 1 hour. So, Kadam, you have a question about the 6th question. We have explained it in lots of detail step by step. Please feel free to email us. Again, this whole session is publicly available. You can go back and check it. Please focus on solving the problems. Again, for anyone who asks follow-up questions, we try to answer them as soon as possible. Even for public sessions, even for unregistered students, we've answered questions for public sessions. We've answered thousands of emails like that. Cool. So let me try to answer this. Okay. So the HTTP pipelining is a technique in which multiple HTTP requests are sent in a single TCP connection, but without waiting for the corresponding responses. Yes. So there is a page called HTTP pipelining on Wikipedia. Those of you who don't know how HTTP pipelining works, you can check it, right? This is exactly what HTTP pipelining is. Okay. This is basically to transfer data faster. That's the whole idea. Okay. So this statement is surely true. Now what about B? It requires 32 RTTs to transmit the base HTML file and 15 objects in a non-persistent HTTP with no parallel connections. Okay, so the keywords here is non-persistent HTTP. So what happens? See, you need 2 RTTs, right? So you need 2 RTTs to send the base HTML file, right? And for the TCP connection, okay, 2 plus there are 15 objects, okay, and this is a non-persistent HTTP connection, which means for these 15 objects, for each of the 15 objects, you need again 2 RTTs. So first 2 RTTs is for creating the TCP connection and to transmit the base HTML file. Then you have 15 other objects. It could be images, it could be anything, right? 15 other objects, because it's a non-persistent HTTP connection, right, with no parallel connections. So you need 15 into 2 because it's non-persistent, right? So you need a total of 32 RTTs. So this statement is also correct. Next, it requires 17 RTTs to transmit HTML base with 15 objects with persistent HTTP. Yes. See, the first two are required for, just like in this case, the first two RTTs are required for transmitting the base HTML file and for transmitting the base HTML file and for your whole for your TCP connection. Then after you have established the connection, because it's a persistent HTTP, each of these 15 objects only requires one round trip time, right? So 15 plus 2, this is 17. So it says 17 RTT, so this statement is also true. HTTP is a stateless protocol. Yes. Okay, that's one of the first statements we describe when we use HTTP. So actually in this case, all the 4 options are correct. Okay, so all AB, again, some of these concepts may be theoretical or maybe even just what do you call it, fact based. Okay, like HTTP stateless protocol, that's a fact based point. Similarly, HTTP pipelining, it's a fact based thing. This is definition of HTTP pipelining, right? So this is what it is. Okay, cool. Let's go to question 9 now. This is also an MSQ, folks. I forgot to mention that. This is also an MSQ. Okay, so multiple options can be correct. This is also very fact-based. Again, there are some fact-based questions about protocols in previous year gates. That's why we are asking these questions, especially application level protocols. And the question is saying which of them are true, not false. Again, the question is which of them are false. Sorry, which of them is true, not false. I think some of you are reading this question as which of them are false. Okay, so please read the question carefully. Again, this is a very fact-based question, very definitions-based question, right? So I'll just quickly answer this. SMTP is a push protocol that uses port number 21. No, it uses port number 25, right? So this option can't be correct. POP3 is a post office protocol that uses port 100. No, it uses port 110. Very fact-based question. So this option is also not right. A mail transfer agent is a software that transfers electronic mail messages from one computer to other computer using SMTP. We have discussed about MTA and MDA in our course videos, right? So this statement is true. Mail access agents use the POP for getting messages from a mail delivery agent. Yes, this is also true. So C and D are correct. These are very definitions and fact-oriented question. Okay. Again, this is all about, do you know about the protocols? Do you know about some of the components that are there in sending mails? Okay. Again, this is trying to test if you know about SMTP, POP. It's trying to ask you multiple statements and questions. Again, this is not hard, but if you don't know these facts, you will not be able to answer, unfortunately. Okay. But such questions have been asked in the gate earlier. That's why we've given this. Okay, cool. Okay, here is an interesting question. This is a numerical type. I actually like these numerical type questions than fact-based questions because I'm very bad at remembering facts personally. Some facts are always okay. Again, this is asking about the fragment offset in the fourth. One second, there's a small typing mistake there. Okay. So please, this is not the byte offset, this is the fragment offset. Okay, I see a bunch of answers, some incorrect, some correct for sure. Again, some of you are asking about question 6. I'll revisit that question after we finish the 10th question so that students who want to leave can leave. Okay. I think that's a better model. So I'll revisit question 6 after we finish. That's a good model to try. Okay, a good chunk of you got it right. I'm happy about it. I thought this was a slightly tricky question, but it's a straightforward question actually if you solve it carefully. Okay, so let me go step by step. Again, my explanations, I'm trying to do them step by step so that you think from first principles. If I were to solve this question myself, I'll do it much faster. Okay, but then you will not be able to understand what I'm trying to communicate. Okay, so what are the facts given to us? The first fact given to us is that the IP packet is 1000 data bytes. Okay, is 1000 bytes, and it has to forward the packet to a network with a maximum transmission unit. Okay, one MTU is 300 bytes. Right, our maximum transmission unit size is 300 bytes. Assume that the IP header is 20 bytes. Okay, so the IP header is 20 bytes. Okay, what will be the fragment offset of the fourth fragment? Okay, so let's break it down first. Okay, what is the maximum data? Okay, what is the maximum data per fragment? What is the maximum data length per fragment? Okay, per fragment, what is the maximum data length? Okay, so let's see. Because your MTU is 300 bytes, the header will take 20. The data that you can transmit is only 280 bytes. That's all you can transmit, right? You can't transmit more than that. That's the maximum. Now you want to transmit a total of 1000 bytes. So how many fragments do you need, right? So number of fragments. So number of fragments that you need, right, is 1000 by 4. Of course, you have to take a seal. This will be 4 fragments is what you need, right, total. Now let's break this down. Remember that the data length, this is a very important fact that people sometimes miss. Okay, so the data length in each fragment must be a multiple of 8. Right, this is important. It should be a multiple of 8. Now imagine in one fragment, if you're placing 280 bytes, what is 280 by 8? So if you think about it, 280 by 8, 280 is exactly divisible by 8. 8 3s are 240. Again, you have 40. Right, so if you divide it by 8, it will be exactly 35. Thankfully, it is exactly divisible. So you have a total of 1000 bytes. Let's break down the 1000 bytes. 280 bytes in the first fragment. 280 data bytes, that's what I mean. Okay, so this is the data, right? So 280, 280, 280 and 160, right? So 160. This is your fragment 1, this is your fragment 2, this is your fragment 3, and this is your fragment 4. Right? You have 4 fragments. Now for this fragment, what will be the offsets? Right? Remember, the question is all about what will be the fragment offset of the fourth fragment. That's the question that's being asked, right? And all of these fragment offsets are like by 8s. So for fragment 0, right? For fragment 0, you will have 0 to 34, right? Because it has, see, 280 by 8 is 35, right? So if you look at the fragment offsets, this offset will be 0. From 0 to 34 will be for fragment 1. What about fragment 2? Let's see for fragment 2. For fragment 2, again, you need 35 of them. So the fragment offset will start at 35 and it will go up to 69. What about the third fragment? The offset will be 70. It will go on to 104. What will be the fragment offset of this? Add 35 to this. It will be from 105 to 124. So the fragment offset is the offset of the first byte that you have, right? So for fragment 4, the offset will be 105. So the answer here is 105. Clear? Simple and clear, right? I hope this is clear. Okay. Number of fragments is 1000 by 4, no, because our data is 1000 bytes. See, our total data is 1000 data bytes. We have to send the 1000 data bytes with each fragment being 280. Right? So it's 1000 by 4, which is 4. Right? So there are 4 fragments. What part of it is not clear? 1 second. Sorry. So the 4th fragment will contain 160, 280 into 3. 1 second. So let's do that. 1 second. Let me just do that. 280 into 3. 280. Let me get my calculator. Okay. So let me just pull my calculator here. Did I do a mistake there? 280 into 3 is 840. 840 plus 160 is 1000, no? That part is okay. What is wrong with that part? I didn't understand. Yeah, so, oh, sorry, my bad. Okay, I got it. This is not 4, this is 280. Okay, I got what I made a mistake. Okay, this is 280. Sorry. Okay, I wrote 4 here. I wrote the answer here. I got it. Okay, so yeah, that's all it is. Any questions here with this? Each packet will not contain look at this. The maximum transmission unit is 300 bytes. 20 bytes is taken by the header, no? So only 280 bytes are left to send your data. Right? So 1000 by 280 is, 1000 by 280 is 3 point something. So 1000 by 280 seal. 1 second. 1000 by 280 is 3.7, 3.5. So you need 4 packets. What's wrong with that? Right? I think that part is clear, right? So let's go to the 6th question. And everybody who wants to leave, you're most welcome to leave because we have completed the 10 questions. 6th question, some people have a concern. That's why I explained it step by step. I knew people would get confused. Okay, so let's again redo the question. 6th question, right? So let's go step by step. I'll redo it from scratch. Okay, cool. So let's see. Consider a TCP congestion control and let the congestion window be 40 KB. Okay, so WC is 40 KB. We know this, and there is a timeout. Right? So there is a timeout. Okay. Next, the propagation time is 50 milliseconds. Okay, which implies one round trip time is 100 milliseconds. Okay, just like the way we explained earlier. And maximum segment size. Okay, maximum segment size is 2 KB. Okay, in the course videos when we solved some of the problems and exercises and also the running example, we used 1 KB. The time taken by the congestion to get back to 30 KB congestion window size. Okay, so let's tackle it. Okay, so as soon as you have a timeout, what happens? Your W threshold becomes WC by 2. Okay, which means it becomes 20 KB, and you do a slow start. Okay, you do a slow start. Okay, so let's go step by step now. Okay, this will take time, but I want to explain it. So let's assume this is the time at which the timeout happened. Okay, this is the time at which the timeout happened. As soon as the timeout happens, we change our W threshold to 20 kilobytes and we do a slow start. When we do a slow start, look at this. When you do a slow start, what is your WC? Your WC is 2 KB. Now, you do your first transmission. So this is your time 0. Let's assume this is your time 0. You change your WC to 2 KB and you do your first transmission. Right? So you do your first transmission. Right? You completed your first transmission, so done. Then after you complete your first transmission, you update your WC. What is your updated WC now? You double it from 2 KB, you double it to 4 KB. Right? Now you send your second transmission. Second transmission is also sent. Then look at this. The third transmission, this becomes 8 KB. Earlier I made a mistake. And I corrected while answering. I wrote 16 KB, actually it's 8 KB. I corrected it also quickly within a couple of seconds. Okay. So next. So then you do third transmission. Okay. After third transmission, your WC is 16 KB. Okay. Then do fourth transmission. Okay. then it can't become 32 kb because your W threshold is 20 kb. So it will get saturated at 20 kb after the fourth transmission. So I'm just writing first transmission, second transmission, third transmission, fourth transmission. It's 20 kb. Okay, let's continue here, right? So after fourth transmission, your WC is 20 kb. Now your so then you do the fifth transmission. After you finish the fifth transmission, now because you have reached W threshold, see this has become 20 kb. Then what do? You increment by 2 kb, which is your MSS. Okay, now your WC becomes 22 kb. Okay, then you do your sixth transmission. Then your WC is 24 kb. You do your seventh transmission. Then you do your WC 26 kb. Eighth transmission. WC is 28 kb. Then you finish your ninth transmission. Then your WC is 30 kb. You don't have to do the 10th transmission. Look at this. If you look at it as time, right? If you look at this as a time axis, from the time of timeout, at the time, as soon as timeout happens, your W threshold becomes 20 kb. You start your slow start, which means your WC is starting at 2 kb. When does WC become 30 kb? As soon as you finish 9 transmissions, right? For each transmission, because the round trip time is 100 milliseconds, you complete 9 transmissions, that takes 900 milliseconds. Some of you are counting the 10th transmission also. You don't have to count it. Think about it as time axis, no? So this is 100 milliseconds, this is 100 milliseconds, 100 milliseconds, so on and so forth. Count it. By the time you come here, it's 900 milliseconds after your timeout. That's what I was trying to explain just a while ago, right? When I was solving it earlier also. Right? I hope you got it now. Right? 1 second. Abhishek, write down this way carefully. You're jumping to 30 kb here, but remember that the starting itself is 2 kb. The starting WC is not 0 kb, it is 2 kb. That's why first write it step by step. First write it step by step this way. That way you'll get much more clarity. Right? So again, you're saying you need initialization. You don't require initialization, no? Because this is congestion control. The TCP connection is already there. The TCP connection is already there. You have a timeout here. Remember, you have a timeout. Right? So if you do a timeout, this is what it should be. Right? I hope this is clear. Starting is 2 kb, no? Starting is 2 kb. So the question is the time taken by the TCP congestion to get back to 30 kilobyte congestion window. It comes back to 30 kilobyte congestion window as soon as the 9th transmission is over. Right? Let's think about it. No, that's why I said people who have finished leave. Others we can sit and discuss here in the chat window. Okay, so I think any questions here? This is what I was trying to explain earlier also. Again, sit down and write it. Okay, is this clear? Okay, I think no more questions here. Good, good, good. Thankfully, again, this is exactly what I've answered earlier, no? Again, find a mistake in what we have just solved right now, no? I mean, this seems logically correct. I don't see a bug in this. Okay, from the time of timeout. So it says at the start there is a timeout. Okay, the time taken to get back to 30 kilobyte congestion window size. Imagine if you're implementing this in code, no? See, the most important thing is, imagine if you're writing the code for the TCP congestion control. Okay, how would you write the code? Let's write the code. Okay, so if that's the concern, we can write the code also. Okay, so when you write the code, what happens? You first update your WC and then transmit, no? That's why I've written this step by step extremely carefully, because I know people could say 1000 milliseconds also. Okay, that's why I'm going step by step here. Right? Is this clear now? Again, I've not seen the answer that others have given elsewhere. I'm trying to solve it in front of you, right? With all of you in the chat window. But as others have mentioned, I've not seen the solution on other platforms. Again, if something is wrong, let me know. I'm here in the chat window. I'm looking at the chat window, Mayank. If there is something wrong, let me know. What if I missed something, I'll correct it. What is wrong here? Let's sit and discuss. I don't see any bug in this. Because imagine if this was implemented in code, no? At the timeout, at this point, what will your WC be? Right? Getting response for 2 KB. That's why we are considering RTTs, no? We are not considering TP. Look at this. We are taking RTTs. Okay, we are taking RTT. We are not taking TP. The whole round trip time, the transmission, the whole round trip time is what we are taking. Right? So again, if there is an error and if you have a convincing argument, do email us. If there is an error, we'll correct it. We are always open to that. Okay. So again, question should be tricky. That's the only way. Again, this is a very small boundary line here. I can completely imagine why some people think it's 1000 milliseconds. Okay. I can completely imagine that. Okay. But if you actually write this timeline step by step and write it, what many people end up doing is they would just simply end up doing, okay, 10 into 100 milliseconds or 1000 milliseconds. But if you think step by step, I think this is a more appropriate answer. Okay. Sounds good. Thank you very much, folks. Thank you for joining in. And yeah, thankfully, I think only a few of you have stayed back for this question. Again, please understand that in public sessions, it's almost impossible to answer every follow-up question. It's impossible, right? Think about it in your university or college, right? I mean, look at it this way, right? In your university, whichever university or college you've gone to, or any other education institution that you've gone to, a class is typically what, 90 minutes, right? A teacher typically spends about 80 minutes with the course, with whatever the content they want to do, and 10 minutes answering questions. We are doing exactly different. We are saying 90 minutes, we have our videos. Go ahead, watch them. Then, if you look at the answers that we have answered tens of thousands of questions. Tens of thousands of questions just in the last 6-7 months. Right? And we are saying, whatever question you have, ask us. We'll try to answer as soon as possible. Like, what more can it be? Okay, so please understand that in a live session, it's impossible to answer everything, because then the whole live session will go for hours together and people will lose interest. Okay. Okay, folks, thank you very much. And again, some of you who are still not agreeing with this answer, please think through it. Please sit on it. If you think there is a better answer or a better explanation, if you think we are wrong, please write an email. We'll respond back to it. Okay. Thank you very much, folks. Bye-bye.